Welcome, everybody. CS201, Computer Science at UCLA. In 2021, last year, UCLA and Amazon collaborated to start the Science Hub for Humanity and Artificial Intelligence. And the mission is to address humanity's pressing challenges by cross-pollinating academic and industry research that harnesses the power of artificial intelligence. And one of the first things the Science Hub did was to select 12 Amazon fellows, all PhD students in the Samueli School of Engineering at UCLA, all of them busy doing their research, all of them doing research one way or the other on artificial intelligence. And I convinced them to all give a round of lightning talks today to talk about what are they doing? What is it that makes them excited? And so we give each of them 5 minutes to give a quick idea of what it is they're working on, who they are, and then we can ask questions while we switch to the next speaker. And my goal is to be done at 5:30, and so come hell or high water, we will be done at 5:30. Everybody gets a chance to speak, and one way you can see who they are is go to the sciencehub.ucla.edu webpage, and there you will see all 12 of them listed. They couldn't quite all be here. I think that at least one just happened to have a doctor's appointment right at 4 o'clock today, and so couldn't be here. But most of them are going to speak. And so if you go to click on research there, you will be able to see the faces and a quick snippet of their research topic. And then today we will get to hear more. And so I am going to go in the order they are listed. So actually we are going to skip the first one, Ruchao Fan, he couldn't be here, but we are going to go with number 2 on the list, Antonio Skiergis. And share your screen if you want, and please go ahead.
Can you see my screen?
Yeah.
Okay. Hello, everyone. My name is Akash, a PhD student from ECE department, and today I'm going to talk about my research, communication efficient and privacy-preserving machine learning. We consider a distributed system consisting of a set of clients are connected to a central server.
So Antonio, just one moment. So it's like your sound is not coming through very nicely over here. It's like a little bit broken up.
Okay, I can use like microphone. Is that better?
Yeah, much better. Very good. Thanks.
Yeah. So we consider a distributed system where a set of clients are connected to a central server in order to solve a statistical problem, such as training a global model or estimating a mean of distributed data or heavy hitter estimation. There are mainly 2 challenges in the distributed system. First is the privacy, as the client's data might contain sensitive information, such as images, location, financial information, or medical records. So the goal of the client is to preserve the privacy of her own data against any curious adversary, including the server and any curious clients. Second challenge is the communication, as the connection between the clients and the server might be band limited or wireless. So the communication becomes a bottleneck for a statistical problem in machine learning. So my research focused on studying the trade-off between privacy, communication, and utility trade-off in statistical machine learning problem. We consider the differential privacy, which is the gold standard notion for measuring the privacy guarantee of any mechanism, where we say that an algorithm A is epsilon delta differentially private if for any neighboring datasets D and D prime, and we say 2 datasets are neighboring if they are differ at only 1 data point. So the algorithm is epsilon differentially private if the output of the algorithm doesn't change much by changing 1 single data point in the data in the entire dataset. So that means the algorithm doesn't depend on a specific item of the client. And the epsilon here is the privacy measure. So when epsilon is small, that means the algorithm is more private. Such of central differential privacy algorithm can be obtained using a trusted server that can collect the data from the clients and adding some artificial noise in order to preserve the privacy of the clients. And this gives a good utility privacy trade-off, but this requires a trusted server in the system. And this might not be feasible in the distributed systems, including federated learning algorithms. So the alternative way is using local differentially private, where each client privatizes her own local data point before sending it to the server. Such of these local mechanisms preserve the privacy of the clients. However, it has a poor privacy utility trade-off. So in order to improve the privacy of the distributed system, we consider the shuffle model. In the shuffle model, the clients send the private data to a shuffler that randomly permutes the private data before passing it to the server. Such of the shuffle model amplifies the privacy of the system and gives a better privacy utility trade-off in comparison with the local model. So we focus on designing a machine learning algorithms that preserve the privacy and the communication efficiency in the shuffle model. Our first paper is to propose a variation of a stochastic gradient descent algorithm to train a global model in federated learning. And our algorithm is communication efficient and private. And at each iteration of this HD algorithm, each client sent a compressed and private gradient instead of sending the raw gradient. And we proved that our algorithm is epsilon differentially private and converges as a function of the total number of samples in the system. And it requires only a few number of bits per gradient. We also apply numerical results to train the MNIST dataset, and we show that our algorithm outperform the best known distributed algorithm in the literature, and it's also privacy and requires only log d plus 1 bits, where d is the dimensionality of the model. Recently, we focus on improve the privacy analysis of the shuffle model, especially for interactive mechanisms that doing multiple iterations on the dataset. And we published two papers, one at SAMCCS conference, and we get the best paper award for analyzing the privacy of the shuffle model. And second one is published in Europe. Now, our research focus on designing an optimization algorithm that converges independent of the dimensionality of the model, because the current model, the private HD algorithm, converges as a function of the dimensionality of the model. Second problem that we are considering is designing a federated learning algorithm to preserve the user level privacy instead of item level privacy. User level privacy means that each user might have a local data set that contains multiple of samples. So when the user is not in the system, the entire local data set of the user, it changes. So we wanted to preserve the client privacy. That means we say user level privacy instead of the item of the system.
Okay, I'm going to cut you off here. So it's perfect timing. Any questions? Any questions? So you can add your questions in chat or in Q&A, whatever is the best way for you to do it, and then I will read out the questions. And that's how we will do it for every speaker. I forgot to say Antonius's advisor is Suhas Digavi, professor in engineering at UCLA, and ask questions. While we set up for the next speaker, you can ask. I see Xiaowei Kai has raised the hand, but I think it's not so easy for you to get to speak. But if you can type in your question, then okay, I don't hear any questions. Let's move on to the next speaker. So thank you, Antonius. The next speaker is Xiji Huang. Her advisors are, she has two advisors, Wei Wang and Isu Sun. And let's see, you want to share your screen?
Okay, sure. Okay, so hi everyone, my name is Zijie Huang. So today I'm going to talk about my research about deep learning for reasoning over graph structure dynamic data. So our world consists of large amount of spatial temporal data spanning from molecular dynamics in biology, information diffusion in social network. It has provided us abundant research opportunities spanning from uncovering dynamic laws from data to accelerating
Hey,
the
Siju,
simulation.
before you say too much more, could you turn on your camera?
Oh, sorry. Uh, yeah, so can everyone see me
Yeah,
now?
yeah, very good. All right, please
Okay.
go ahead, go ahead.
Okay, so yeah, so these like abundant data have give us abundant opportunities from uncovering dynamic laws to accelerating simulation process. However, reasoning over spatial temporal data is non-trivial due to the complex interplay of both spatial and temporal properties compared with static graph modeling. So a very simple example would be how to predict the trajectories of a five-body spring system with fixed graph structure. So existing neural network-based methods employing graph neural network to approximate pairwise object interactions, which reveals how system changes from timestamp t to timestamp t plus 1. Despite their good performance, there are still several challenges needs to be addressed. The first challenge lies in how can we learn under non-uniform data distributions. In realities, we have many situations where we need to deal with spatial temporal data that happen at irregular space and irregular time, such as like the movement of Ubers. So irregular space means the observations for different agents are not temporally aligned, and irregular time means the observations of a specific object can happen at non-uniform intervals. To tackle these like challenges, one of our work proposed latent graph ODE model, which models the latent dynamics using neural ordinary differential equations, consider the mature influence among agents. It can like simultaneously learn the high dimensional embeddings for object trajectories and in the meantime infer like all of their initial states simultaneously to capture their mature influence. So for this model, we have conduct experiments on like the following three data sets over two tasks, which are interpolation task and extrapolation task over variance observation ratios. And like from the experiment results, we observe that our model is able to make good predictions, especially when the data is relatively sparse. So this is the first challenge we identify. And the second challenge lies in how can we efficiently model the complex interplay of spatial and temporal properties. In the previous five-body spring system example, we assume the graph structure remains unchanged, but in reality, graph structures can change over time with node attributes, and they will pose significant mature influence to each other. So how to learn under like involving graph structure remains relatively challenging. What's more, sometimes we may only know like observe the trajectories of individual nodes without knowing the underlying graph structure. So in this way, we need to infer the graph structure first and then utilize the graph structure to make the prediction. So given a concrete example, let's think about the spread of COVID-19 where nodes are 50 states in the United States and ages on the daily mobility data among states. So essentially both nodes and ages evolves over time and they will influence each other. So our second work, coupled graph ODE, tries to build a model that considers a co-evolution of nodes and ages in a continuous manner. Because many existing methods are usually like discrete, they may not well capture the underlying dynamics for like continuous systems. So to capture the continuous mature influence, what we did is to decide to coupled ODE function for nodes and ages respectively. And we also conduct experiments on the COVID-19 dataset and also the social network opinion migration dataset. And we are especially good at making long-range predictions. And also we conduct one like case study to study how like different mobility intervention policy can affect like the diffusion or like the spread of COVID-19. So it can be beneficial for like the government to make some public policies. So like in the future, I'm also interested in like utilize deep learning techniques for accelerating simulation and also accelerating neural network training from like a dynamic system view. So yeah, thanks everyone.
Thank you. Questions, everybody. I'm sitting here looking for questions in the chat and looking for questions in the Q&A, and I'm ready to take your questions. I will read them out loud if you type something in. But meanwhile, of course, we can always set up for the next speaker. So Yifan Kiao, you are next. You can share your screen while Shiji can still take questions. Do I hear any questions? Please, everyone, stay around so that if questions come later, that you're here to take them. But otherwise, let's move on to the next speaker, Yifan Kiao. Here you are, advised, as it says here, by his two advisors, Harry Xu and Miriam Kim. And please.
Cool. So I assume like my screen is visible?
Yeah.
Cool. Yeah. So hello, everyone. My name is Yifan Qiao, and I'm a third-year PhD student advised by Professor Harry Xu and Miriam Kim. Today, I'm going to share my research on machine learning systems, which aims to democratize large-scale machine learning training with higher efficiency, lower costs by developing full-stack systems, covering training algorithms, operating systems, and cloud infrastructures. So large-scale machine learning model is a double-edged sword. On the one hand, it powers many applications. For example, large models make better recommendation, beat top human players in games, and help programmers by auto-completing the code. However, large-scale models are also notoriously expensive to train due to their intensive resource demand. For example, GCN is a graph model working on large graphs, and GPT-3 is a large language model. Both of them are widely used in industry. However, it is estimated that training them on large datasets takes TBs of memory, hundreds of GPU years, and costs millions of dollars. Such a high cost prevents general users to adopt large models. So my research thus is trying to tackle this problem by developing full stack systems with co-design. We know that machine learning models run on top of multiple software and hardware layers, including the model itself and the framework, the underlying infrastructures like operating systems, virtual machines, and cloud instances, and hardware in the lowest level. My observation here is that co-designing across multiple layers reveals a lot of new potential benefits, including cross-layer optimizations, efficient use of cheaper resources, and better performance isolation. Here, I will show my work Doreless as one example towards the direction. Doreless is a graph neural network training system, leveraging serverless threads on cloud. The problem is that training a graph neural network, or GNN, on large graphs is very expensive because it requires a lot of GPUs. Our insight here is that at the infrastructure level, which is shown in the third level here, serverless paradigm can be a more cost-efficient solution. This is because serverless threads offer massive parallelism and a flexible pay-as-you-go pricing model. Here, I take AWS as an example, where they name their serverless threads as AWS Lambda. As we can see, CPU servers, which is shown here, plus serverless threads are more than 5 times cheaper than the GPU counterparts, make GN training affordable. So keep that in mind. We co-design the algorithm to make it more efficient for serverless threads. we proposed an asynchronous training algorithm that creates a deep pipeline from the GNN model. The pipeline helps overlapping the computation and communication between CPU servers and serverless threads. Further, we build a Dorless framework, which not only helps users build GNN models easier, but also takes the pipeline as input and separate it into fine-grained graph computation tasks and tensor computation tasks. Finally, we map the different tasks we map the graph computation tasks to CPU server and the tensor computation tasks to the serverless threads, making both of them being fully utilized. Taking them all together, Dorless is 1.2 times faster and 4.8 times cheaper than GPUs and still guarantees convergence. My other work, Canvas, take a further step as an efficient and fair data plane for co-running machine learning workloads. It co-designs the runtime, the OS, and the network scheduler to improve the throughput and reduce the performance variation. To conclude, I think full stack systems with co-design enables a lot of potential optimizations and provide better performance and lower costs, which I believe will help us democratize large-scale machine learning to everybody eventually. That's the end of my presentation. Thank you, and I'm happy to take questions.
Thank you. Questions? I am looking in chat for questions, and I see one. How much is the pay-as-you-go pricing?
Oh, yeah, that's a good question. Actually, like I forgot the actual number, but it's about like 0.000067 per invocation for a single Lambda thread. And the price increases if we allocate more CPU resources and memory resources. But like that's fine because like as a pay-as-you-go pricing model, we don't pay this price for all the time of the execution, but only for the time where the computation is highly paralleled, and we do that. So with this flexible pricing model, we can still enjoy the best of both worlds, the affordability and the high performance.
Thank you. Other questions? I saw that we had one answer. We had one question for the previous speaker that was answered in the chat. That's also fine. Can do it that way too. Okay, I say many thanks, Yifan. And so that gives us a chance to move on to the next speaker, Harold Lee. Do you want to share your screen?
Yeah, hi everyone.
Yeah, let me just say Harold Lee has one advisor, Kai-Wei Chang, and yeah, go.
Yeah, okay, hi everyone. I trust that you can see my screen.
Yeah, we can.
Yeah, okay. So I'm very happy to share my research that is learning vision language alignment from natural data. So both language and vision are the most effective devices with which people communicate. And researching both natural language processing and computer vision towards many real-world applications would benefit from complementary knowledge from both modalities. So for example, current NLP models are now trained only on text. So without visual knowledge, these ungrounded NLP models will fail to solve problems require real-world experience. One famous example is the reporting bias, where NLP models believe that black sheep are more common than white sheep because people tend to only mention the colors of sheep when they are rare, which is black. So meanwhile, state-of-the-art computer vision systems are typically trained to predict from a fixed set of object categories. For example, the widely used dataset COCO has only 80 object classes. And it is a open research question on how to generalize to rare objects in the real-world application, for example, detecting holes on the road. So single modality models have a restricted view of the world. NLP models lack visual world experience, while classical computer vision models only recognize objects within a limited concept pool. And my research offers a multidisciplinary solution. we seek to create an alignment model that maps the visual world to the rich natural language world. So we propose to utilize rich natural data, that is millions or billions of images, text, and image text pairs from the internet, because they record and describe the world we live in, and they can be easily collected from the internet and requires little human annotations. So my prior research has developed methods to learn vision and language alignment, not only from aligned image text data, but also unaligned images and the text data. And learning such vision language alignment models bring multiple benefits. First is that they facilitate many practical applications that involve the intricate interplay between vision and language. For example, visual question answering, medical diagnostics, and disinformational meme. So here I give two examples. For example, the application of visual question answering could be to help blind people navigate with their daily lives, because they can now take photos on their phones and ask questions. Yeah, it can also help doctors to better treat their patients. Okay, so besides direct application to many domains, it can also serve as a bridge, grounding NLP models to the visual world, reducing the reporting bias problem we just mentioned. In our most recent work, they can also, learning a vision language alignment model can also enable computer vision models to be semantic rich and generalized to virtually any possible concept in natural language. So in our recent work on object detection, we can convert the traditional detection problem into a vision language grounding problem, where the model is given a natural language instruction and try to ground entities in the images. So this enables pre-training on millions of image text pairs, and our method can zero-shot rivals with many supervised baselines without annotated data. And that's all for my research. Thank you.
Thank you very much. Questions out there? Questions? Very good. Thank you. Let's move on to the next speaker, Michael Kleinman. His advisor is Jonathan Cao. And Michael, do you want to share your screen? Yes, you do. Okay.
Can you see okay?
Yeah, it's good.
All right, perfect. So hi, my name is Michael, and I'm excited to talk about some of my research on usable information and evolution of optimal representations during training. I'm going to focus on one project, but I feel like it sort of represents the ideas and the things that I'm interested in working. At a high level, we were interested in studying how relevant and irrelevant information is being represented during training. By relevant, we mean the information that's necessary for performing the task. So in the input above, it would be the features associated with the dog, whereas the irrelevant information would be the grass or the background. To study this, we needed to develop a good summary statistic to quantify the information contained in a representation. And we also study how the learning dynamics are affected by the implicit regularization coming from stochastic gradient descent from using large learning rates and small batch sizes. There are a couple possible reasonable learning dynamics or learning motifs that a deep network could undergo. We might expect, under some measure of information or decodability, that the relevant information about the input increases or becomes more decodable or usable through training. In contrast, we might expect that the irrelevant information remains as decodable or accessible as it was originally. A different hypothesis is that while the relevant component of the information is increasing, the irrelevant component of the input decreases monotonically during training. And finally, an alternative hypothesis is that early in training, while the relevant information is being learned, some irrelevant information is also learned. And later, when the network realizes that it doesn't need this information, it discards this information. This last hypothesis was proposed in recent work, but crucially, information was quantified using Shannon's mutual information. And later work disputed some of the findings and claimed that the observed learning dynamics depended on how mutual information was approximated. This led us to rethink how to compute the information in a representation so that we could have a meaningful summary statistic of the representation. And the key idea here was that in general, a representation can store information in different ways. So it's possible that the information is easily accessible or usable, so that a simple decoder, like a linear one, could read out the information. But it's also possible that the information is present in the representation, but there requires a very difficult transformation to actually read out this information. And mutual information makes no such distinction to how the information is represented. This motivated us to define the usable information in a representation as the information that's available to a simple decoder, so that the usable information between a representation Z and label Y is defined as the entropy of Y minus the cross entropy loss of a decoder Q trying to predict the true distribution P. And we show that the usable information is a lower bound on the mutual information. So to apply the usable information to study how relevant and irrelevant information is being represented during training, I'm going to show you a quick example. So we looked at the learning dynamics of CFAR 10 images, but to do this, we had to modify the tasks slightly. So instead of asking the network to output the standard labels, we defined an arbitrary course labeling, splitting the classes into two arbitrary groups. We then asked the network to output the course label. And this allowed us to study how the semantically meaningful information, so the information about the true classes, the information about the 10 original classes in CFAR 10 was being represented while the network was learning the solution to the course labeling task. We found that as the validation accuracy was increasing, the usable information about the course labeling, so what we trained the network to output, increased to about 1 bit. But what was very interesting was that the information about the fine labels initially increased, even though we didn't explicitly ask it to, and then later decreased, so that by the end of training, it only had the relevant information about the course labels. And last, it's often believed that the implicit regularization from stochastic gradient descent from the use of small batch sizes and large learning rates is important for generalization. So we investigated how increasing the batch size affected the minimality of the representations. And we found that for large batch sizes, the network didn't form these minimal representations. Similarly, when we decreased the learning rates, we also found that the network did not converge to these minimal representations. So to summarize, we introduced the notion of usable information, and we used it to study how minimal sufficient representations emerge during training. And we found that the implicit regularization from stochastic gradient descent was important for learning these representations. Thank you.
Thank you. Questions? We have another one of those where a question was asked in the chat and the previous speaker has been typing in the answer, which is wonderful. While we're setting up for the next speaker, any questions? Yeah. We can always take more questions later. But otherwise, let's go on to Akash Singh, another PhD student in the School of Engineering. His advisor is Mani Srivastava, and over to you.
Thank you. Hello, everyone. My name is Akash Singh, and I'm advised by Professor Mani Srivastava. The theme of my thesis is deep scene understanding using RF and its fusion with other modalities. Now, when we talk about scene understanding, we talk about perception, analysis, and interpretation of dynamic objects around us, shape of the rooms that we are in, how objects are moving with each other, and how objects are interacting amongst themselves. Traditionally, most scene understanding tasks happen using cameras, and no doubt cameras are some of the best sensors that we have. They are really good at segmentation, classification, tracking, and recognition. However, cameras suffer from some very fundamental challenges. While cameras can tell us a lot about the scene, they can tell us about the facial structures of human beings, emotions, they can tell us a lot of information about objects, vibrations, sound, etc. They suffer a lot in bad weather conditions, when there is smoke or fire, and in low light conditions. Research is ongoing on how to improve the performance of cameras in these settings, but it's anybody's guess when that will conclude. Additionally, cameras are also not good at seeing things behind a wall or any other object. This becomes particularly important in scenarios such as first responders during a fire, earthquake, hurricane, etc. Additionally, even if I see an object from the outside, I have no idea whether this object, in this case a camera, is on or off. Is it streaming a video or images? Who controls this camera, or who's the vendor of this camera? Or what is the field of view, or like how much of the scene is this camera capturing? So even though cameras themselves give us a lot of information about the environment, this is not sufficient, especially when we are beginning to design these autonomous agents, which need as much context as possible. This is where my thesis comes in. I call this deep scene understanding. By deep, I mean we need to go beyond what cameras can see. And it also alludes to the algorithms or the family of algorithms that I'm using, which is deep learning. Now let's look at this very complex scene. Just by looking here, you can make a lot of assumptions or like you can guess what people are doing. And when I talk about deep scene understanding, I really care about the following things. Firstly, I want to recognize activities being performed by different objects or agents in this scenario. I want to detect hidden devices. They may be hidden to us, they may be placed by an adversary, or they may be hidden just because we cannot see them, but these devices can be important in case of first responders. Again, like if there's a fire, I want to know if there are cameras present in the building, and if I can access them, that will really help my cause. I want to detect the activity of devices. Is somebody taking videos or pictures illegally? Is somebody making a phone call? This will give me a lot of information about how attentive they are while crossing roads, etc. I also want to detect objects. I want to track objects. I want to project object states into the future, like what would happen after 3 seconds or 4 seconds becomes particularly important in self-driving use cases. I want to detect concealed devices for safety use cases. And finally, I also want to extract 3D scene features. Again, very important for autonomous agents. So the key enablers for deep scene understanding are detection of object activities and states, localization and tracking, and finally, complex event detection. This is where RF comes in. Now, RF is already present all around us. Wireless communication, passive sensing, and so many use cases, all our mobile base stations already have RF. Secondly, as we begin deploying 6G, we will already have this RF sensing capability present throughout the world. Finally, RF devices can be used in a non-intrusive manner. You don't have to wear anything. They are more privacy preserving than cameras. RF data is not human interpretable. RF can work through foliage, fog, obstructions, and low light. And finally, RF information can complement vision systems. The key facets that I want to target in my thesis are human activity recognition, detection of internal states, concealed objects, 3D scene reconstruction, etc. Some key projects that I have worked on during my thesis include, firstly, human activity recognition using RF sensing. This is particularly challenging because unlike cameras, RF sensors are point scatterers, which basically means that in a room, you hardly have 100, 200 points reflecting back, whereas cameras give you millions of pixels. So you do not really have a dense representation of the scene using RF, and thus this sparsity problem makes any kind of sensing challenging. So we take these point clouds, we pre-process them, we pass them through our deep learning algorithms, and finally we are able to detect activities being performed in a room. Secondly, most of you must have felt this, like if you go to this like a shady, cheap Airbnb, you might feel that somebody has placed a camera somewhere. So how do we detect these hidden objects? Like you walk into a hotel room, you open your phone's app, and the app directly tells you if there's a hidden camera, microphone, motion sensor, etc. in the room, and where exactly it is located. This is what we have done again via RF sensing, in which we sniff wireless packets being transmitted by these devices. And we use these packets and a ground truth sensor to basically correlate our activities with the traffic of these devices to detect and localize them. Finally, moving on to a more sensor fusion theme, we fuse—
Yes, and brief.
We fuse a single camera image with millimeter wave point clouds to estimate dense depth of the scene. That is it for my talk. Thank you so much. If you have any questions, I'll be more than happy to answer them.
Very good. Thank you. Questions, as usual, ask them in chat, ask them in Q&A, or we can take them later, up to you. But meanwhile, we're setting up for the next speaker. Any questions? Otherwise, the next speaker is Weitong Jiang, and his advisor is Chen Gu. And here you go.
Yeah, let me first unmute myself.
Always a good idea.
Yeah, I see my screen.
Yeah.
Yeah, hi everyone. I'm Weitong Zhang, and I'm a third-year PhD student advised by Professor Chen Gu. Unfortunately, received the fellowship, and thank you for being here. My research interests are mostly focused on building the explainable and accountable reinforcement learning systems. In detail, I'm seeking the theoretical explanation for the popular algorithms and designing new algorithms with theoretical guarantees. So I'll discuss some detailed topics in my research, but since this is not quite a long talk, I won't cover the technical details in my projects, but I'd love to discuss that with you after the talk. So the first topic I want to introduce is the reinforcement learning with functional approximations. So, like the reinforcement learning has achieved great success in various tasks like the Go games, self-driving, and so on. And many reinforcement learning tasks, the agent should intensively interact with the environment and frequently update its policy. And like the reinforcement learning tasks also have a very large state space. For example, the Go game has almost uncountable, like 10 to the power of 360 possible combinations. So if you want a feasible algorithms, it should be use functional approximation, like the deep neural networks to compress the state space and extract the features. But it's not well understood how to efficiently explore, learn, or exploit the system information using functional approximation. And some things like the deep Q network or the policy gradient remains in the mystery from theoretical perspective. Therefore, my previous work answers some detailed questions regarding how to use the functional approximation for the reinforcement learning. So the first question is like, can we well explore the environment without the guidance of the reward function? So this reward-free exploration is quite an interesting paradigm. For example, if I ask you to firstly explore the office without doing anything, then I ask you like, can you get a pen from the office? What should you do for the first time exploration? In my recent paper, I answered this question by proposing an algorithm which can efficiently explore the environment with linear functional approximation. The second part is, the approximation errors always exist in all functional approximations, from linear functional approximations to deep neural networks. But how will the functional approximation errors impact the performance of the algorithms? Previous work only showed like if the error is large enough, we cannot learn anything from the functional approximation. But this is not aligned with our intuition. In practice, we all know like the error always exists. So in my recent work, I provide an upper bound under which like the functional approximation error cannot affect the performance of the algorithm. And I also propose an algorithm dealing with these functional approximation errors. Besides this, I'm also conduct some works on the representation learning in reinforcement learning, like how to select good representations from all possible features and to deliver good performance. Furthermore, since neural networks are widely applied in modern reinforcement learning, we apply the frontier theory of deep neural networks and provide a theoretical guarantees results to well explore and exploit the environments using neural networks. Finally, I'm also curious about how to leverage the causal structure, like the causal relationships between those features to improve the robustness and accountability of reinforcement learning. In addition to those projects, I also work as a core member on a project predicting COVID-19 tendency using machine learning, where our forecast is reported to the CDC for the policymakers, the suggestion for the policymakers. Moreover, I'm also collaborating with Professor Chung Liu's group in the Department of Chemistry, predicting the properties of chemistry reactions using deep neural networks. I believe like all of these projects will have a broader impact in related fields. And that's the very end of my lightning talk. And thank you for listening.
Yeah, thank you very much. I'm still out there looking for questions. We have a question for the previous speaker, the scene understanding and IF speaker. So maybe you can go and answer in the, that's on a Q&A in this case, if you can find it. Any questions for this speaker here? Meanwhile, we can set up for the next speaker, of course. And people, of course, are most welcome to also to save their questions for later if that's what their preference. So maybe what we do here is that we move on to our next speaker, who is Xing Zhao. Her advisor is Veronica Santos. And do you want to share?
Yes. Hello, I'm going to share my screen. Just a moment. Okay.
Yeah, okay. It's coming through. Great.
Yeah, sorry. Can you see my screen? Yeah.
It's very good. Yeah.
Okay. Yes. Okay. So hello, everyone. This is Xing Zhao. I'm a PhD student from the Biomechatronics lab working with
Professor. Jing, let me just say that you clicked on something so we can see all your text and stuff. I think it's enough if we just see your main slide.
Okay, sorry. Let me see. I think I made a wrong screen sharing. Okay. Is that going to
that looks great. Yeah, let's go with that one.
Okay, thank you. All right. So today I'm going to present 3 of my projects regarding the human-involved haptic robotics. The first of my project is for the semi-automated robotic packing. I designed the optimal poses for a bimanual robot to stably grasp on different shaped engine parts, and also I developed the manipulation sequence with inverse kinematics for the grasp, inspection, and placement with the robot. I also integrated the vision and the human robotic collaboration component. A video is showing here. It should be showing. Yeah. On the top, it shows the simulated and the physical component of the manipulation, and to the right shows the human collaboration user interface. And my second project is for human upper limb motion analysis. So as you see in the left, we collected the data from human searching of buried objects using their hand and arms within a sandbox. After that, I developed an analysis framework and used the combined unsupervised inference and supervised classification to extract primitives and spatial temporal patterns from the human data, which can be used to reformulate and design bimanual robotic motions. The project I have recently proposed and currently working on is for tactile-driven assisted button fastening. We all know that dressing is an important activity of daily living, and buttoning requires fine motor skills that can be difficult for people with impairment. Although there are robotic studies about how to better place clothes on human for the assistive dressing, there is no existing work on the assistive buttoning. Therefore, I propose the work instead of directly manipulating buttons, I will design a robot to hold a button hook and leveraging the tactile information with motion controls. We will use a mannequin wearing a shirt for the early stage development of algorithm, and in the study provide multisensory integration, including the vision for stock and tactile perceptions. The framework for the control of the robotic garment fastening is as is shown in the right. We will collect data from human demonstration, then design the motion primitive for the approaches, phases, and tactile-based regression model and the reinforcement learning model for the buttoning phrases. After our algorithm has been developed and test safe on the mannequin, we will move on to implement that on the human. However, it is reasonable to assume that people, especially the older adults, can feel uncomfortable being approached by a robotic arm and especially holding a button hook. In this way, we propose to also develop a framework to improve the user experience. We will study how different levels of situational awareness and the human supportive action can affect the human subjective trust, as well as their measurement of risk and workload. We will also collect real-time data regarding the gaze monitoring and physiological data, such as ETA and heart rate, to study their real-time trust and experience. In this way, we will hope to improve their collaboration with the robot. So in summary, we will build a tactile-driven and multi-sensory framework for the assisted button fasting, and also design the participant experience to improve their collaboration. This project will address the following fundamental robotics challenges, including how to allow a robot to use human to approach human bodies, to manipulate deformable objects, and to develop the trust between human and robot. That is the end of my project, and I will appreciate your comment and questions.
Very good. Thank you very much.
Yes.
Still looking for questions if anyone has any. Otherwise, we can slowly set up for the next speaker.
Okay.
And thank you again.
Yes, thank you.
I think we.
Yeah, I will stop sharing. Let me just figure out where it is. Sorry. Yes.
Yeah. So let's see. I think the next speaker is just about ready. I think the next speaker is Tao Meng. No.
Yeah, but Xiangning, you can go first, maybe.
You want to go first? We can arrange that. So
oh, sorry,
so Tao Meng,
sorry, I forgot I thought that it was me. Yeah, let me stop sharing.
Okay, so everything in its own time. Let's move on to the next speaker here. So once we get the screen sharing switched, perhaps.
Yeah. So can you share a screen right now? I think you can just pause my screen.
I think you need to maybe unshare. Would be a good move.
Okay.
All right. So the next speaker is Tao Meng, and his advisor is Kaiwei Chang. And over to you.
Can you see my screen now?
Yeah, it's good.
Okay. So hello, everyone. Today, I'm happy to share my research about constraint inference for bridging the distributional gap in natural language processing. My research focused on a concept called distributional gap, which means the distribution in model predictions is deviated from that in the ground truth. This phenomenon widely exists in real-world applications when we deploy an NLP system to real world. Basically, there are two scenarios. First, training data is not drawn from the same distribution of the test. Usually, this is because the test domain is naturally low resource and we can hardly get data from there. A classical example is cross-lingual transfer, where we train an NLP system like parser in English and apply it in some low-resource language like Urdu. Second, NLP models nowadays are pretty large, like BERT large, GPT-3, and so on. We expect that one model can apply in different tasks and domains, since training a very large model for a specific domain is very computationally expensive. Therefore, such distributional gaps widely exist, and this may cause systematic errors. To solve this problem, my solution is to leverage constraints. Constraints are a set of rules for the model predictions. Basically, it is compiled from the domain knowledge or from the human experts, and we want the model predictions to satisfy the constraints. Here is an example in cross-lingual parsing. When we train a parser in English and apply it on Hindi. In English, the parser learned that in the 8th position non-link, 8th position is usually on the left, which leads to a mistake when we parse a Hindi sentence. However, if we inject the constraint about the property in Hindi, we can correct this. Basically, in this case, with proper word order constraints, we are able to boost the cross-lingual transfer accuracy from 34% to 53%. In my research, I aim to answer 3 research questions. First, what kind of constraints can better bridge the gaps? Second, how to formulate the constraints. Third, how to incorporate constraints with natural language processing models. My goal of the research has 3 dimensions. In results, I expect the constraints are able to guide the model to make predictions in our expected distribution. In method, I expect various of NLP models are able to incorporate the constraints efficiently, like we don't need to retrain or fine-tune the models. In practice, I expect the constraints are easy to acquire and effective yet controllable. For example, in the parsing example, I'm actually able to control the probability that the 8th position is on the left. So far on this direction, we have some progress. We successfully inject word order constraints in cross-lingual transfer dependency parsing, inject gender ratio constraints in mitigate gender bias amplification, and design an integer linear programming framework for mining constraints from data. In the future, we plan to expand our research to natural language generation area and design frameworks to mine more general constraints from data. That's all for my presentation. I'm happy to take any questions.
Very good. Thank you very much. Questions out there? I see that there's a pattern today where some people ask questions in the chat and then the previous speaker types in the answer while the next speaker is speaking. That's very good. I can work with that. But type in as you like, either in chat or in Q&A. And otherwise, maybe we can quietly move on to the next speaker. So now it is indeed Xianying Chen.
Can you see my screen? Hello. Okay, so my name is Xianying Chen, and I'm currently a PhD student at UCLA Computer Science Department. And thanks a lot to Amazon and Science Hub for the fellowship. And it's my honor to talk about my research, which is mainly the automated machine learning. And I will first introduce the effort to automate the neural architecture design, which is a previous main focus of AutoML in the past several years. So the neural architecture design plays an essential role in the development process of deep learning. For example, in computer vision, the mainstream architecture evolves from AlexNet to ResNet, then to the recent transformer. And apart from the accuracy of the architecture, the efficiency, such as inference speed and number of parameters, also matter a lot. And previously, such design is a trial and error process, which requires tremendous experts' efforts and computational resources. So the research question here is that, can we automate such process and discovering high performance architectures without manual intervention? And pioneers in this field develop prototypes based on reinforcement learning and evolutionary algorithms due to the discrete nature of the architecture space. But those methods usually include full training and evaluation procedures for each sampled architecture to obtain the essential reward signal or the fitness. For example, to search for an image classifier on CFAR, and both methods consume thousands of GPU days. So their computational overheads are prohibitive for practical usage, especially on large-scale tasks. And our previous works lie in the stream of inefficient architecture search, which mainly relies on the continuous reduction and the weight sharing mechanism. And with such gradient-based update, we can finish the architecture search within 1 GPU days. However, such method has encountered several problems. And from the figure, you can see that as the search proceeds, the searched architecture can perform worse and worse. And finally, this method will end up with an architecture filled with all of skip connections. So we have several papers to improve and stabilize such search process to enable a stable and efficient architecture design. So it mainly comes from 2 perspectives, SuperNet training and architecture selection respectively. And the main intuition is we resort to learning and architecture distribution and propose a division-based architecture selection algorithm. So automating the architecture design has already achieved great success, and many automated discovered architectures like EfficientNet has already been deployed in real-world applications. And so our next question is that, can we also automate the optimization process of the entire machine learning pipeline? So as a first step, we explore the field of learning rate schedule, because the schedule plays and can have a big impact on the final performance. And where we leverage a graph neural network-based controller to generate the learning rate schedule. And the figures here show our learning rate policy across different language tasks. And our approach can greatly improve the fine-tuning accuracy of BERT compared with handcrafted like cosine or linear decay policy. And apart from the learning rate schedule, we also aim to discover better optimizer. People has already been using LMW and like Momentum SGD for a long decade, but whether they're the optimal solution remains unknown. So recently, we showed that on Vision Transformer, the accuracy can be greatly improved from a purely optimization perspective, and revealing a huge headroom for the optimizer perspective. And another evidence is demonstrated by a previous work, Shampoo optimizer, that can improve like both the accuracy as well as the convergence speed by using second order information. So we think this direction is of vital importance, as nowadays people keep scaling up the model and data in both such as language and vision domains. So training those giant models is extremely resource and time consuming. So besides just discovering optimizer that can achieve like higher accuracy or lower perplexity, we believe that discovering optimizer that can enable faster convergence speed and learning, just faster convergence speed using AutoML is a very exciting topic. Yeah, and that's all my. And thank you for listening. And
oh, thank you very much. Yeah. And I think I forgot to say your advisor is Choju Shea.
Yeah.
And yeah, thank you. I see again somebody typed in a question for the previous speaker, and there's answers given in text, which is very good. But maybe it's time to go to the last speaker, the most graceful person today who goes last without complaining, Xinyu Hu, whose advisor is Isu Sun. And please.
Yeah, thanks for the introduction. Hello, everyone. My name is Xinyu Hu. I'm currently a fourth-year PhD student, and today I'm greatly have the honor to present my work on differentiable symbolic reasoning with graph neural networks. So existing deep learning works have shown that it has successfully settled many low-level and tasks that doesn't require the complex reasonings. However, for the type of the question that are more focused on high-level reasonings, such as pseudocode or logical reasonings, the model usually needs to plan and reason in the discrete symbolic space at high level. And even human needs a long time to think the answer. However, it is difficult for existing deep learning models to directly accomplish these tasks. To accomplish this, there's a trend of work called neurosymbolic reasonings. Most symbolic systems are non-differentiable, such as SAT solver, logical inference, etc. The system cannot learn end-to-end and still require an intermediate discrete parsing step, which requires lots of annotations. Therefore, with like in the deep learning era, when we collected lots of the data, most likely end-to-end model can compete these kind of neurosymbolic reasoning methods. Based on these limitations, our solution is that whether we can explore the graph neural networks can be used as a differentiable reasoning modules. As we know, graphs are a very efficient abstract of modeling discrete knowledge. Since its introduction, graph neural networks have been proven to be very effective in automatically extracting effective representations from structured data. So we will explore whether it can be used as a differentiable inference module over the structured data to do the symbolic reasonings. My work so far can be divided into two parts. The first direction is to use the relational graph neural networks to model symbolic knowledge. Relational graph data can model very complex knowledge. For example, many works based on knowledge graph have shown to solve complex question answering tasks. In this kind of graph, nodes are labeled with multiple types and edges between nodes have multiple relationships. To effectively model the relational graphs without manually design of some templates or metapasses, we propose a heterogeneous graph transformer. This model can implicitly model the semantic structure of the graph with few listed parameters and can automatically learn the most useful metapaths for different tasks. And it achieves a sort of performance on some benchmark datasets. Although HGT model can effectively model relational structure data, it is also difficult to generate to some tasks that lack labeled data. Compared with expensive labeled data, we can easily obtain massive unlabeled data, either it is a graph or the other types. Based on this, we have done a series of works on graph self-supervision and trainings. The most representative work in this line is GPT-GNN. Our goal is to learn transferable representations through self-supervised learning of graph neural networks so that the downstream tasks can only utilizing a very small number of samples to achieve good results. Our idea is to use the graph generation task to do the self-supervised learning. If the model can reconstruct the graphs from scratch, it can naturally capture the overall distributions. The bigger difficulty in this process is how to balance the dependency between the node generation and edge generation. We propose a factorized attribute generation objective to model such interaction. The second research direction is to conduct symbolic reasonings over the relational graph. Let's take a question answering system as an example. Like answering complex questions, relational reasoning is required to do some logical expression over the knowledge graph and directly walk through the knowledge graph to obtain the answer. But this approach relies on the quality of the knowledge graph. However, existing knowledge graph is still very incomplete and rely on experts to maintain. Our first trial is to hope that a neural network can implement the differentiable reasonings by itself. As a first attempt, we explore whether the knowledge in the knowledge graph can be used as training data so that a language model can obtain the ability of relational reasonings by itself without accessing a knowledge graph. We linked the wide-known Wikidata with the Wikipedia to synthesize some question answering data points to pre-train the models, and it achieves very good results on many open domain question answering tasks. The final trial is that after we tackle the simple relational reasonings, we further explore whether the model can conduct more high-level complex logical reasonings. Our goal is to conduct the first-order predicate logic as a task. For example, the task of listing the presidents of all European cities that have never hosted Olympics. We borrow the great idea of fuzzy logic system to implement fuzzy logic operators so that it can fulfill a wide range of important logical properties while it is totally learning free so that we didn't require any complex queries to train these operators. Thanks for the listening.
Thank you very much. This brings us to the end. Any questions for the last speaker? Of course, you're most welcome, but otherwise at this point, I will open up for questions for all the speakers. And I still see some questions and answers going on in chat. The only promise I make is that we'll stop by 5:30 or we will stop before that if the questions run out. So I'm looking in chat, I'm looking in Q&A to see if you have questions. But let me take the chance to say thank you to all the speakers. Thank you to some of the people who are online. My name is Jens Pausberg. I am the director of the Science Hub. We have Kathleen Allen from Amazon on the call. We have Stefano Soato from Amazon and from UCLA on the call. And many of the advisors whose name you have heard fly by on the call, and some of them have been typing in answers to help with answering some of the questions. There's a question about whether the slides will be available. So this is a good idea. That's something that also has struck me, that we should have an entry on the Science Hub website. And one way to have a memory of today is to collect all the slides into a single file, so we can see them there. That's something we are looking into. I would like to get that done. Other questions? Technical questions are welcome as well. What do you say? Any questions? It was wonderful to hear all this progress. So so the exciting thing here is that these are all the speakers are sort of in the middle of their PhD studies. They're neither beginning or neither ending. They are all in the middle. They all have more time to go at UCLA, and I think are bound to produce more results than all the ones that they present today, and to pursue the plans that they talked about. So it looks like the future is bright, and that more is to come when we have these events again in the future. But I must say, I don't see so many more questions. So maybe it means that we are done for today. So one more big thank you to the speakers, to Edna for making the technical stuff work, to Shuyang for also making technical stuff work, and just thank you everybody. And we will have another event one time in the future. Maybe next time it'll be in person, who knows? But I'm happy we could all get together on Zoom today and hear what's going on. So thank you, and goodbye.
Thank you, everyone. I'll be working on the recording for the website. It will be on the website later on tomorrow afternoon.